and welcome. Today we're going to talk about covariance and correlation. We can start by examining the Swedish stock market, or OMX40, where we can see that in 2008 the stock market as a whole went down by quite a lot. In 2009 and 10 it went up again, quite substantially. In 2011 it went down again, and in 2012 it increased in value again. If we assume that we invested 100 Swedish crowns in the stock market in the year 2008, then we can see a decline in our value the first year, then an increase the next coming 2 years, a decline again during 2011, and an increase during 2012. We might also be interested in looking at some other returns, for example for TeliaSonera, which experience a little bit the same pattern, with decrease in 2008 and 2011, an increase in 2009 and 2010, and a decrease in 2012, which was then different from the whole market. We can plot that one as well, but what's most interesting is actually to look at these two together. And we do that here, because here we can see that the first year, both the market as a whole and TeliaSonera went down by quite a lot. The next year, during 2009, both went up by quite a lot, and about the same amount. But then, during 2010, the Telia went up only a little bit, but the market went up quite a lot. They both went down during 2011, and here in 2012 they actually took different directions. So maybe this is even easier to examine in the table of the numbers. So here I've computed the average return, which is marked by R bar. And we can see that the average return of the market was slightly positive, and the average return of TeliaSonera was actually negative. But the interesting part is when we compare the year by year. So here, for example, in 2012, we see that the market went up, it performed better than its average, and TeliaSonera actually went down. So they went in different direction this year. During 2010, the market went up by a lot. TeliaSonera also went up by a little bit, but I mean, it's clear that the market went up by quite a lot more than Telia did. But on the other hand, in some years like 2008 and 2011, they performed pretty much the same. In 2008, both went down by a lot, and in 2011 they both had quite substantial decrease in their value. And the reason we are interested in this you will learn during the courses you take in finance, but basically it has to do with diversification effect. We want sometimes assets move in the same direction, and then having more of them doesn't really help our risk because they all move in the same way, up or down. But in other years they move in opposite directions, so if I then only own one and I'm unlucky, I get the bad one. If I own several, sometimes these movements cancel out each other and my total risk will be decreased. Anyway, a measure of this co-moment is called covariance. Covariance is denoted as COE or cov of x and y, or by the sigma x comma y. So the important thing here is that we always have a covariance between one asset and another asset, or two random variables x and y. And that's why we have this x comma y to denote which two variables are co-moving. Just a reminder, variance was denoted as sigma x squared, and standard deviation was denoted as sigma x. So it might be a little bit confusing, because all three of these use the Greek letter sigma, and it's quite important to distinguish between what is covariance and what is variance. But one way to do it is to remember that if you have only one subscript like x or y, then it means it measures movement of a single asset, in this case the asset x, or any random variable x. When you have the covariance, you always have two different random variables, or two different assets in finance then, and that's why you have the x comma y. So they look a little bit the same, but they are different, so it's very important to separate them. Okay, the covariance can take any value, basically. It can be very large negative, it can be very large positive. And it's also expressed in the same units as variance. It's like percentage squared or squared Swedish kronor or something like that, which makes it very hard to interpret. And since it's hard to interpret, we don't really like it. Instead, we usually look at the correlation coefficient for x and y, or just the correlation between x and y. And I'll show you in a moment what values that one can take. The correlation coefficient is denoted rho, or it looks like a p, but it's a Greek letter. And again, you have this x comma y because it's the correlation between x and y. The good thing about the correlation coefficient is that it can only take on numbers between -1 and 1. So it can never be, for example, -50. It's always between -1 and 1, and that also means that the closer you are to 1, it means that they are correlating more with each other. And the closer they are to -1, it means that they are going quite a lot in opposite directions. If the correlation would be exactly 1, you would say that they are perfectly correlated. If the coefficient would be exactly -1, then you would say that they are perfectly negatively correlated. And another good aspect of this is if you get any other number than -1, or any number outside the interval -1 and 1, then it means you made some error in your calculation. So if you get a correlation of 1.5, something's wrong, so you need to check your calculations. Okay, a little bit more on the notation before we get to the formula. We had several notations for expected value. For example, we used the e of x and also the Greek letter mu. But now when we talk about covariance and correlation, we're going to look at x and y at the same time, so just using mu for expected value would be very confusing. Instead, we're going to use the subscript mu of x and this y to denote if this is the expected value of x or the expected value of y. And I will choose this mu notation instead of the e because it takes a little bit more space if you have the e of x. Okay, so the formula that we're going to look at for covariance now looks like this, and replacing e of x and e of y with the mu, it would become like this. So just as with the variance calculations, we measure the deviation of x in one outcome from the expected value of x. But instead of taking the squared, as we did before, we multiply it instead by the deviation of y from its expected value. So that's how you get the covariance in case these two move in the same direction. So if both are better than its expected value, then x is a positive number and y is a positive number. If you multiply a positive number with a positive number, you get a positive number. So going in the same direction gives you a positive covariance. And this is also true if x would be below its average or its expected. This would be a negative number. And if y is below its expected, this will also be a negative number. And again, negative times negative is positive. So whenever they move in the same direction, you get a positive covariance term. On the other hand, if they go in different directions, let's say that x is better than it's expected, so this is positive, while y is worse, so it's negative, then you would have one negative number times one positive number, which is negative. So the covariance will have positive impacts from when they move together, and when they move in different directions, then you will be adding a negative number. So if you have a very high negative number, then probably usually they went in different directions, and the opposite if it's very highly positive. Just as with the variance, we multiply each element then by the probability of event j happening. Just a quick notation if you take or have taken some other statistic classes. This is a simplified version of the covariance formula, but it will be sufficient for most classes in finance, at least at the bachelor level. And the reason is that we usually look at, for example, how does the stocks go in case we have a good economy next year? How much does stock X go up and how much does stock Y go up? And when you assume that there's only one possible value for X and Y given a good outcome, then any covariance formula would become the simplified version. But it's good to know that this is not the proper formula. If we write it out on a different form, which might be easier to follow, it would look like this. It's very similar to when we had the variance formula, and for that reason I'm not going to perform any example with this, but it works just as it did with the variance. So the mu of x is the expected value of x, the mu of y is the expected value of y, the p1 is just as before the probability of event 1 happening, whereas x1 and y1 then is the outcome for x and y respectively in case of event 1. So we look at the deviation of x when event 1 happens from its expected value. We take that time, the deviation of y from its expected value for the same event. We multiply these two together and then we weight it by the probability of event 1 happening. Then we add the same thing for event 2 and as many events as we might have. Okay, so when you estimate covariance using historical data, because remember in the variance movie, we said that if we just observe that the market went up by 15% one year and down by 50 another year, we don't really know what the actual probability was, so we cannot use the probability formulas. Instead, you use the following formula, which is similar then to the variance formula. You take the average of x instead and the average of y instead of the expected value. You take the outcome each year minus the average for x times the outcome of y in the same year minus the average of y. And then we divided it by n minus 1 after summing all of this. And this was for some technical reasons that you can learn in your statistics class. We can put these two formulas on the same side if we want. Just as with the variance, we replace all the expected values by the arithmetic averages. And we remove all of the probabilities because we don't know them. Instead, we divide by n minus 1 in the end. Okay, so let's take an example with this. We have looked here at the OMX and Telia in the beginning of this video. So let's compute the covariance of them. Okay, so this is how I usually put it up in Excel to make it easier to follow. You always want to take the outcome of the x variable, which is in this case the OMX30. So this one is the x and this one is the y variable. You want to take the outcome of the x variable in this specific year minus the average value of this variable over all years. So we have the average returns down here. You can compute them as before. And to find then the this part, we take the outcome in this year minus the average return. And if you remember from the variance video, we lock this in using the dollar signs like this, which enable us to simply repeat the same calculation for all years. So here, for example, in 2010, we've taken the outcome here, F6, minus the average return. And you can see here that in 2008, the OMX40 performed 53% worse than the average return over all years. So it's a deviation from the expected again. For y then, we can do the same thing. We take the outcome of Telia in 2008, we subtract the average return, we lock this in with the dollar signs, and we can then take this little corner to the right and draw it down. Sorry. There we go. Okay, so the difference then is that even though Telia had a minus 35% decrease, the deviation from the mean is only 32%. Why is that? Well, it's because the average return is actually negative for Telia during these years. To compute the covariance term, then, we were supposed to multiply these two with one another. As we see down here, we should take this value times this value. So, we take the deviation from the mean for x times the deviation from the mean for y. We can again draw this down, and we get deviation in all years. Okay, so the only year when they had different signs, so here they are both negative, here they are both positive, both negative, and in 2012 was the only year when they went in opposite directions, but then the covariance term is very small, so we don't really see it, although it is a negative number. Okay, to finally get the covariance, we are supposed to sum all of these, so we start by that. We can use the built-in function sum, or if you have a Swedish Excel, it's called summa. We take the sum of this cell down to this cell, which you can use the colon for. We add it together, and the covariance then, after summing all of this, we should divide it by n minus 1. So we take this number, and we divide it by the number of years we had, which was 5, minus 1. So the covariance between OMX40 and Telia during these 5 years is 0.08 and so on. And we have no idea if this means they were highly correlated or not. So, what we need to do now is to find the correlation instead of the covariance. Because the covariance was hard to interpret, just as variances, they have strange units, and also it can take really any number. It's very hard to say what it should be. But the correlation coefficient was always between minus 1 and 1. So if it's close to 1, it's close to perfect correlation. If it's close to minus 1, it's close to perfect negative correlation. That's why we usually look at the correlation coefficient in case we want to know how well they are co-moving. So, how do we compute this then? Well, the formula looks like this. The rho stood for the correlation, or the correlation coefficient between x and y. Here we have the covariance between x and y. And now, this is the nice thing, we standardize it by using the standard deviation of x and the standard deviation of y. Why do we do that? Well, if they are moving, if the covariance coefficient, the covariance value is high, it could be because both assets are moving a lot up and down, so they might not be covariant very much after all. But here we adjust for their individual volatility or individual standard deviation, which makes the correlation coefficients always be between -1 and 1. Okay, so let's compute the correlation then between TLS-NERA and OMX40. So here I've prepared everything that we had done before, and the formula we needed then was the correlation. To get the correlation, we needed the covariance, the standard deviation of x, and the standard deviation of y. So I'll calculate them, and I also color-coded them, so the covariance is purple, the standard deviation of x is green, and the standard deviation of y is blue. So now we simply have to follow this formula. The correlation is supposed to be the covariance divided by the standard deviation of x times the standard deviation of y. And remember, if you have multiplication like below an division sign, you need parentheses around it when you want to enter it into your calculator, or as in this case, Excel. We find that the correlation between TLS-NERA and the market is 0.87, and this means that they actually do Kumo quite a lot, these two. Okay, so that's it for today. I hope you are now able to solve anything related to covariance or correlation in your exercises. Thank you.